So this part of the presentation actually it's going to be very interesting and very understandable, I promise you. Okay, so quantitative analysis part 1. Now the first thing we need to know is there's things we need to know, okay? So there's must-know core concepts that have to be reviewed and absorbed, right, before we can approach quantitative analysis. Once familiar with these facts, analysis will be rather straightforward and simple. So here we will consider 8 core concepts. Now, look at these concepts this way. So suppose you get a job and your friend's working there already, okay? And the boss comes out and gives you a 5,000-page book, big, thick book. And he says, these are all the regulations you need to know to work here. Okay, then the boss walks away. You feel a little daunted. And your friend walks over and he or she says, you know, there's really only like 2 or 3 things you need to know to work here and be successful, right? Well, that's a good friend. So in quantitative research, there are hundreds of little facts and stuff like that, right? But there are certain core concepts that you just really need to know to do quantitative analysis. So that's what we're doing here. We're giving you those key things to know, just like the friend breaking the 5,000-page book into, you know, a few statements. So here are the 8 core concepts. Now we're going to go through each of them one step at a time. All right, so you can see that the BANA 2013, we conceptualize quantitative data analysis as 7 separate steps, right? That's our take, our conceptualization, right? So the first is a study map. You're just writing down the relationships between variables you're going to examine. All right, intuitive. Data entry, right? So we got, say, you know, surveys, and we have an SPSS database, and we have to enter the data from the surveys into the SPSS database, make sure they're in there correctly. Step 3, checks of data integrity, making sure the data are appropriate for analysis. You say in the book we mentioned, it says, you know, it states, I had an old football coach, he would say, you can't start with chicken feathers and end up with chicken salad, right? So you can't start with data that's not appropriate, you know, for the tests, for the statistical analysis, you know, and come out with quality findings, right? So checks of data integrity are checks for missing data, statistical power, test assumptions, the validity, reliability of the instrumentation, the measurements, right? Very important step. Then univariate analysis, step 4. That's where you're looking at one variable, you know, at a time. You're analyzing one uni meaning one variable at a time. You know, so if we're looking at class attendance, you know, that's one variable, class attendance. How many days does the average person attend class, right? So it's more like the getting to know you phase. You're getting to know the data, one variable at a time. Okay, then bivariate analysis, step 5. You're looking at that, the one-on-one relationship, generally between, you know, a predictor and the outcome, you know, an independent variable or covariate variable with the dependent variable. So if it's, you know, the predictors, how much do you enjoy class, that's related to how often do you go to class attendance. Those are 2 variables, the one-on-one relationship, you know, bi meaning 2, bivariate. And then 6 is multivariate analysis. So we take several predictors and see what their joint effect is on the outcome. So if you look at how much do you enjoy class, did your doctor prescribe, you know, taking meditation class, you know, do you go to the morning or afternoon, and we regress those predictors on how often do you come. We see which is the strongest one, right, through the step 6. And then step 7, write up and report, right? So there you go. Now, Albert Einstein, right? So he said education is not the learning of facts, but the training of the mind to think, right? And that's what these 7 steps are. It's not just facts, right? It's a way to think about quantitative data analysis, a way to train the mind on how to do quantitative data analysis, right? You do this first, you do this second, you do this third, right? So where do you start? You know, where do you go? Where do you stop, right? So it's a way of training the mind of how to do it. So the focus here, right? The focus here, right? We're going to be doing quantitative data analysis. So we're going to focus on step 1, mapping out the relationships, and then steps 4, 5, and 6, which are doing the actual statistical analysis, right? There's a whole other 6-week webinar, you know, going through each step, right? A little bitty. So we're going to be going through these main steps right here, right? And that's okay. The data is going to be already entered by the administrators. We'll mention some of that's step 2. Step 3, the checks of data integrity. We'll mention some of those, and then we'll focus on steps 4, 5, and 6, right? Which will be the actual quantitative statistical analysis, which is what we're after. And then step 7 here, we're going to be doing that when we write up the mixed methods, right? We'll write up the mixed methods, write up and report together. So we'll see that too. Now, the must-know core concept 2, parametric versus non-parametric statistics, right? So statistics are often broken down into 2 families. The first being parametric statistics, right? These are things, you know, we'll look at, you might have heard of them, t-test, correlation, ANOVA. They're based on equivalence of variance, right? How scores vary together equally. As you could imagine, you need generally a bigger sample size to get an equivalence of variance, right? So they're tests that makes assumptions about the data, such as are all the scores in a continuous variable distributed normally, right? And usually, like I said, the more people you have, the more, you know, equal the distribution, right? So they make assumptions about the data that have to be met, you know, to use the test, essentially. Then non-parametric statistics are tests that examine, typically through rank, the relationship between variables without making as many assumptions, right? Probably the most widely used one that we'll use here too is the chi-square. So it's a little less stringent. So the bottom line, usually people like to use parametric statistics if the sample size is big enough, and they generally, you know, use non-parametric statistics when the sample size, you know, doesn't have enough power to use the parametric statistics. So if you have a small sample, you might lean more toward non-parametric statistics. Now, we're going to go through both. Why? I'm glad you asked. We're going to be going through both because sometimes that sample size might be right on the line, right? So you might say, well, I have 30, you know, sample size is 30, which isn't really big. So it may be appropriate for parametric statistics, but I'm not sure it might be more appropriate for non-parametric statistics. So it's actually not unusual to apply both, right? So there's parametric and non-parametric equivalents to each test. So if you're right on the line like that, you might like to do both, right? And you may, per se, report the parametric statistics in a paper, but also mention that non-parametric statistics were also applied, the equivalent tests, which also, you know, probably, most likely, they usually do, produce the same findings in terms of statistical significance and so on. So what that illustrates is, even if the assumptions were not met that well, because, you know, we have a small sample size, we also applied non-parametric statistics which didn't have assumptions, and they produced, you know, like results. So that bolsters our confidence in the findings when we have, say, a smaller size sample where we're presenting non-parametric and parametric statistics. This all will become a lot more evident when we actually do it, right? So, remember what Aristotle said, we learn, in our doing. So once we do this, that will become a lot more evident, but for now, it's a little contact theory, right? You hear it once, then the next time you hear it, it's more familiar. So, must-know core concept 3, descriptive versus inferential statistics. Now, descriptive, right, key word, describe. They're describing variables, right? It's also the univariate statistics. Remember that step in the 7 steps, right? So you're just describing variables, one at a time, right? Descriptive statistics. Now, this differs from inferential statistics in that inferential statistics infer. So descriptives describe. Inferentials infer. Infer what? Right? That's the question. So think about if you have a sample. You're going to get findings, relationships between variables within this sample. Now, the sample is from a population. So what we'd like to do is generalize from the sample to the population, right? So if variable AB is related in our sample, we want to infer those findings to the population. So if A and B are related in the sample, we want to infer and speculate that A and B are also related in the population. So we're inferring with the statistics from our sample to the population. So those are the inferential statistics. Now, a lot of the big decisions, right, in quantitative analysis are based upon the level of variable measurement, which is must-know core concept 4. So generally, people recognize 4 levels of variable measurement. Okay, so you can see I've slowed down. So that means, so listen up, listen tight. All right, so we have 1 nominal, 2 ordinal, 3 interval, and 4 ratio. Okay. Like I said, a lot of the decisions in quantitative analysis, what tests to use and all, are based upon recognizing these levels of measurement. All right, 1, nominal. So it's categorical, right, putting people in categories, but categories that can't be ranked. So you could, per se, in gender, you could put people in categories male and female, right, 2 different categories, but you can't rank them. You can't say 1 and it should be higher than the other. And then 2, we have ordinal, which are categorical variables that can be ranked. Right? So we could rate something as poor, fair, good, excellent, all categories, and you can rank them in terms of, good and bad, top to bottom, bottom to top, right? It's also important to realize in ordinal, there's no equal spaces between measurement points, right? So that means that the measurement point distance between poor and fair doesn't have to be the same as good and excellent, right? It's all conceptual and almost somewhat arbitrary, right? So the distance in between fair and good and poor and fair, are not necessarily equal, right? And also we want to mention, because we're talking about categorical variables, that the dichotomous variable is, you'll hear that term a lot, is a categorical variable with 2 categories. It could be ranked, unranked, could be male, female, yes, no, good, bad, anything like that, right? But it has 2 categories. It's called dichotomous. Now, interval. So here's where, as the scores go up and down, they're showing a greater or lesser presence of something, like in our depression example, 1 to 5, right? So as it goes to 1, there's less depression. As it goes to 5, there's more depression, right? So it goes up and down. It's the greater and lesser presence of something, right? The scores are measured along a continuum. Now there's equal distances along measurement points, right, like an IQ test. So the distance between a score of 90 and 100 is 10, and the score between 100 and 110 is 10, right? There's equal distance between measurement points, but there's no true zero. Right? Like in an IQ test, if you get a 0, that doesn't reflect a total lack of IQ or intelligence, depending on which construct you think is represented. A ratio is the exact same thing, except there is a true 0. So it's measured on a continuum, equal distances between measurement points with a meaningful true 0. For example, weight. If you're measuring weight and there's a 0, it does reflect an actual absence of weight. Okay. Now, in the real world application, right? So when you do research, people don't really say these terms. They say categorical and continuous. Is the variable categorical? Is the variable continuous, right? Categorical meaning nominal ordinal, continuous meaning interval ratio. Okay, 5, you have to be able to, identify a study variable type, right? So we have an independent variable. That's also called a predictor variable. That is our predictor of interest. That explains the dependent variable, right? And of course, the dependent variable is the outcome variable, the variable we want to explain, right? Or that's being examined. So if the outcome is class attendance, we're trying to explain that. We think the big predictor is, whether you're assigned a morning or evening schedule. That's the predictor of interest. That's going to explain if you go to class or not. Now, a word about covariate variables. They're not mentioned as much as independent and dependent variables, but they're very important, right? Sometimes they're called predictor or control variables, right? So it's a variable in a data set that may not be the focus of the study, right? So it may not be, the target, right? But it has to be included in analysis because it has a significant impact on the dependent or independent variables, usually the dependent from what I find. So why are covariate variables so important, right? So consider this. Suppose we relate to being assigned a morning or evening class, right, the independent variable on the left, right, morning or evening class assignment, to the number of, right, the dependent variable, the number of days you attend class, right? And we find that it's significant, which is generally notated by probability less than 0.05, right? It's a little notation we'll discuss later. But, so we find at this bivariate level between the two variables a statistically significant relationship. So that's good. If we walk away now, we believe that class attendance is a function of being assigned morning or evening classes. So if we walk away, that's what we believe, okay? However, if we're doing, say, a multivariate procedure like regression, and we decide to control for a covariate such as how much you enjoy that class, right? All of a sudden you'll see the less than sign becomes greater than 0.05. So what's that mean? That means that there's no longer a significant relationship between assigned class time and attendance, right? So what happened is the relationship between class time, assigned class time and attendance was explained by class enjoyment. That means if you enjoy the class, it doesn't matter what time you were assigned the class. So if we walked away without controlling for the covariate, we would have been misinformed, right? So this is saying it doesn't matter what time you're assigned the class, it matters your level of enjoyment, and that's going to decide if you're going to go or not, right? So see the asterisk. So in this case, you could say that the covariate variable class enjoyment predicted the dependent variable attendance over and above the independent variable, making it non-significant. Now think about it. If you don't add the right, the appropriate covariate variables, then and you don't control for those factors, you could be totally misinformed and think one thing, class attendance is a function of one variable when it's really the function of another. So covariates are very important. So core concept 6, moving along now, okay? So hypotheses, right? Just going over a few rules for a clear hypothesis, because if we're testing the hypothesis statistically, the hypothesis must be clear, or we're going to have a hard time, forming the right statistical test, right? So one rule is present one relationship at a time. So sometimes you'll see a hypothesis that might say residents that attend evening classes are happier, healthier, and more optimistic than residents who attend class in the morning. This is really 3 hypotheses, right? You want to be able to say if a hypothesis is supported or not supported. So if the first factor, right, they are happier, but they're not more optimistic, there's a conflict there. So the hypothesis is supported in one way and not another. So you can't definitively say the hypothesis was or wasn't supported. So it'd be better to break them up into 3 hypotheses. Residents attending evening classes are happier than those attending morning, right? Number 2, residents attending evening are healthier than in the morning. And the last one, residents attending evening classes are more optimistic than residents who attend morning classes, right? Because you can state definitively, if each one was or wasn't supported, independent of the other. Now, the cause and effect relationship, right? It's important to identify the cause and effect between the variables. You can do this many times with the if-then test, right? So if we apply it to our hypothesis, we could say if residents are assigned to evening classes, then they will attend class significantly more days per week relative to residents assigned to the morning classes, okay? We didn't state that our hypothesis this way, but it's always good when you can, because then the cause and effect is clear. And lastly, make it as specific as possible. Right, so a vague way of stating our hypothesis. Class scheduling will be significantly related to class attendance. Right? So a little vague. So more specific would be assignment to morning or evening class, right? That's class schedule, but it's more specific, right? Will significantly impact number of days per week residents attend class. So that's class attendance being measured as number of days per week. Right? So sometimes it's nice to what you call operationalize, right? Operationalize, the variable. So for example, attendance is operationalized by looking at the average number of classes attended per week. And it's also, like I said, that's good for statistical analysis because you could see exactly how to measure it and how to relate it. All right. Now here's a big one. You don't hear these combined too often, but it's real important. Okay? This is a big bit of knowledge. So, must know core concept 7, the 3 dimensions of a variable relationship. Okay, so whenever you look at the relationship between 2 variables, you need to consider these 3 dimensions. 1, significance, 2, directionality, and 3, magnitude. If you do that, you'll be real comprehensive in your analysis. So 1, significance, specifically statistical significance, right? You're looking at the probability that the findings, the relationship, the findings are a result of chance, right? So in terms of significance, you would call a relationship statistically significant, again with the notation P probability is less than 0.05, or not statistically significant, P is greater than 0.05. Now, if there's one thing that's harped on in the world of qualitative research, it's this statistical significance, okay? So, you'll be seeing it a lot. So what does by chance mean, right? A lot of people, they know that it has to be 0.05 or less to be significant, but, you know, the further you get from, you know, Stats 101, the more that by chance, you know, starts to fade a little many times, right, me included. So, for our sake, I guess, right, I've put down here, by chance means it appears that there's a significant relationship, but there really is not. Okay? So, in statistics, 0.05 probability reflects that we're willing to accept that in 5 times out of 100, findings will appear significant, but are not. They're actually by chance. Okay? So what's that mean? So, for example, taking a practical example, there's a man in an office, and a client signing a form. The client has a piece of pizza. I guess you don't have to hold it like the man in the image to the left is, but he's asked to hold a piece of pizza while the other man signs a form, right? A coworker walks by, never saw this guy with the piece of pizza before, right? And he says, hey, I didn't know you like pizza, right? And the man says, I don't like pizza. You just happened to see me holding this slice by chance, right? It's even in our everyday vernacular, right? By chance, right? So essentially what happened is the relationship looks significant. You see someone holding a pizza, yeah, of course it looks like there's a relationship where the person likes pizza, a significant relationship between the person and pizza. But it's only the appearance of significance, right? So that's a by chance, right? So when we look at it statistically, we're saying if we conduct 100 statistical tests, right? So we have 100 statistical tests. They're all statistically significant. They're all 0.05 or less, right? We know conceptually that 5 of those out of the 100 are not real significant relationships, but have only occurred by chance. So basically we know there's 5 stinkers in that whole list of 100 that's saying, hey, this is related to this when it's really not, right? So that's our level of probability, right? So just like we got faked out by the guy holding the pizza, it looks significant. There'd be 100 tests, they all look significant, but 5 of them will just be by chance. So statistical significance, right, for our purposes, because it could be less than 0.05, right? But typically it's 0.05. So is the relationship significant? If P is less than 0.05, it is. If it's greater than 0.05, it is not. Our first consideration. All right, next. Directionality. So directionality in a variable relationship is either positive or it's negative, right? A positive relationship between 2 variables means as one increases, so does the other. So if we score a level of class enjoyment and that's going up, if it's a positive relationship with attendance goes up. A negative relationship between 2 variables means as one goes up, the other goes down. So if scores for enjoyment go up, class enjoyment go up, and it's a negative relationship, class attendance goes down as those scores go up, right? They go in a reverse direction. So the negative relationship is often portrayed by a minus sign in front of the statistical coefficient. And if there's no minus sign, it's usually a positive relationship. For example, on the bottom, you see for the Pearson's R, the correlation, if R equals negative 0.35, there's a minus, it means it's negative. As the one goes up, the other goes down. If there's 0.35, right, and there's no minus, it's positive, meaning is one score goes up, the other score goes up, right? So here you have it encapsulated. Minus sign is negative, no minus sign, usually positive. Now magnitude. Remember when I said there was a focus on statistical significance. Many times in a study, the authors will say, for example, variables 1, 2, and 3 were statistically significant in relation to the dependent variable, and these other ones weren't, right? And that's where they'll end, just in terms of identifying statistically significant relationships. That leaves out a big part of the story, as we will see, right? So the magnitude reflects the strength of the relationship between variables. And that is as exciting as it sounds, okay? So how impactful is one variable upon the other, right? So the magnitude of a relationship can be indicated in several ways, such as the effect size, very popular one, which we will use right here. So 3 dimensions, magnitude. Important note on magnitude. The relationship between variables might be statistically significant, but have such a small effect that the relationship is almost inconsequential. So it could be significant, but almost not matter still, right? Or it could be significant and really, really matter, okay? So thus, the effect size is a huge consideration, which is often not considered, right? So as it says here, all significant relationships are not equal. Consider, right? Consider. We will illustrate. What factors impact class attendance, right? Suppose you're going, you have the option of going to meditation class, right? 3 things you believe significantly impact your decision. The first, your emotional well-being. Do you wake up, you're happy, you're cool, right? Hey, I don't need class today. And another day you wake up and you're like, woof, a little on edge, right when the eyes open, maybe I should go to meditation class, right? The second one, weather. Is it good or bad, right? Because you're walking to class per se. Maybe you don't like the sun, maybe you don't like the rain. And a hair day. So you want to look presentable. You have a good hair day, you might go down there. A bad hair day, maybe you're having a bad hair day, you don't care if it gets messier, so you go to class, right? So